Welcome to the deep dive. Today we're jumping right in. Silicon's been amazing, the absolute bedrock, but it's starting to feel its age, wouldn't you say? Especially for the flexible, super efficient gadgets you'll want tomorrow.
Absolutely. I mean, the push for smaller, faster, it's relentless. Moore's law is hitting fundamental limits, and that's where we need, well, new materials.
Exactly. And that brings us to this challenge with 2D materials. We have great N-type ones, right? Like almost 222, they move electrons well.
Right, they're fantastic for electrons.
Yeah.
But for the kind of digital circuits we rely on, CMOS logic, you need both types. You need a good P-type partner, something that carries the holes.
And finding high-performance, stable P-type materials, that's been the real sticking point.
It really has. It's often called the P-type bottleneck, and it's genuinely held back progress on advanced low-power 2D circuits.
Okay, so that sets the stage. Our deep dive today is focusing squarely on a material that looks uniquely positioned to break through this bottleneck, tungsten diselenide, Wse2.
That's the one. A very promising candidate.
So our mission here is to unpack why. Why WSC22? What are its core properties? How are researchers tackling its main challenges like contact resistance?
And ultimately, what do these breakthroughs actually mean for the future? For flexible electronics, wearables, low-power tech that, you might actually use.
Right. So let's start there. Why WSC22? What makes it stand out from the crowd?
Well, intrinsically, it just has the right stuff for holes. Its band alignment is really favorable for efficient hole transport. That's fundamental for good P-type performance.
Okay, the basics are right.
And crucially, it's stable. Unlike some other contenders, like black phosphorus, which degrades pretty quickly in air, WSE22 holds up much better. That makes it way more practical.
That environmental stability is huge, isn't it? Removes a major headache. But what about its structure? You hear about these 2D materials being like sheets.
Yeah, think of it like a nanoscale sandwich. You've got a layer of tungsten atoms right in the middle, squished between two layers of selenium atoms.
A WCC sandwich.
Exactly. And within each layer, the atoms are bonded really strongly. Covalent bonds. Very robust. But the force holding the different sandwich layers together is much weaker. Van der Waals forces.
Ah, so that's the key to flexibility. Strong within, weak between.
Precisely. It means you can peel these layers apart relatively easily, exfoliate them down to incredibly thin sheets, even a single atomic layer thick. Think of it like peeling layers off graphite to get graphene, but with WSE2 under.
So you get these ultra-thin, flexible sheets, but the sheet itself is still strong.
That's the idea. And it gets even more interesting when you get WSE2 under in down to just a single monolayer.
Just one sandwich thick.
Right. Its electronic properties actually change quite dramatically. It transitions from an indirect bandgap semiconductor to a direct bandgap one.
Okay, and why is that significant?
Well, the bandgap also increases to about $1.68 of the naira. This direct, wider bandgap makes it much better at interacting with light. So, great potential for optoelectronics, things like light detectors or emitters.
Fascinating stuff. But you mentioned challenges. What's the biggest hurdle for actually using WSC2 in transistors?
Yeah. It's the same big problem that plagues most 2D material transistors. High contact resistance.
Contact resistance. So getting the electricity into and out of the WSC22.
Exactly. It's like a microscopic traffic jam right where the metal contacts meet the WSE22 channel. There's an energy barrier there called a Schottky barrier that makes it hard for the charge carriers, the holes, in this case, to flow smoothly. It really limits performance.
A bottleneck at the junction. So how are researchers getting around this? How do you fix a traffic jam at the atomic scale?
Well, there are some pretty clever strategies. One really effective approach is called molecular or chemical doping, essentially treating the WSE22 right under the contacts.
Doping the contacts, how does that help?
It effectively thins out that Schottky barrier, making it easier for the holes to tunnel through. Researchers have found some really effective dopants. Platinum chloride, PTCl422, is a standout.
PTCl42 is a standout.
PTCl422s. It achieves incredibly low contact resistance values. We're talking record lows around $0.23 km. Omega, nu M Mabella. And critically, it's stable for months. And it's CMOS compatible. That's a big deal for potentially integrating with existing manufacturing.
Compatibility is key. Are there other doping methods?
Oh, yes. Things like nitric oxide, NO, have been used to get really high on currents in the transistors, which means more signal. And bromine, or tendiprotos, is interesting because it can be applied using solution processing.
Solution processing, like printing.
Potentially, yes. It opens doors for potentially cheaper printable electronics, not just relying on complex vacuum deposition. And it's not just chemical doping. Some groups are using other materials as contacts, like niobium-doped WSE2 itself, to get ultra-low resistance too.
So a whole toolkit of solutions emerging, and this is leading to real performance gains. What kind of numbers are we seeing?
We really are. We're seeing whole mobilities, how quickly the holes move, it's even up to around $205 for model layers.
Which is pretty fast for these materials.
It is. And crucially, the on-off current ratios are excellent, often better. That means the switch works really well clearly on, clearly off, which is vital for digital logic. Low leakage.
Okay, so high mobility, great switching. This really does sound like it addresses that P-type bottleneck.
It really does. It means we now have both high-performance N-type, MOST-IC, and P-type, WSE 2D transistors. We can finally put them together to make complementary circuits, like CMOS inverters.
The building blocks of digital logic.
Exactly. And people have built them. We've seen WSE2 NOSTI CMS inverters achieve, well, frankly, astonishing voltage gains up to 1280 in some reports. Or, alternatively, achieving ultra-low static power consumption down to just tens of picowatts, like
40 picowatts. That's incredibly low power. So what does this actually mean for you, the listener? What kind of applications could this enable?
Well, two big things jump out. First, that ultra-low power CMOS capability is huge for extending battery life, and everything from wearables to sensors. Second, remember that weak van der Waals bonding between layers?
Yeah, the flexibility.
Right. It means WSE2 devices can be inherently flexible. You can build transistors on plastic substrates, maybe even paper someday, that keep working even after being bent thousands of times.
So truly wearable, bendable electronics, integrated into clothes, or maybe medical sensors that conform to the body.
That's the vision. And combined with those solution processing techniques we mentioned, using dopants like bromine or iron thiochloride, if we saw $2-3, it points towards potentially low-cost, printable, flexible circuits, moving beyond rigid silicon and expensive fabrication labs.
So wrapping this up then, WSE22 seems like, well, a really crucial piece of the puzzle for post-silicon electronics.
I'd say it's a cornerstone material. It's stable, it has the right electronic properties for P-type transport, and crucially, researchers are finding really effective ways to overcome that contact resistance hurdle.
Enabling these high-performance devices.
Definitely. Now, are there still challenges? Of course. Scaling up production from tiny lab flakes to large uniform wafers is a big one.
Manufacturing at scale.
Right. And ensuring stability not just for months, but for years under real-world operating conditions. Plus, seamlessly integrating these new materials into existing manufacturing processes. That's all work in progress.
Sure, the path from lab to market is always long, but it feels like we're at a really pivotal point here.
I think so. We're genuinely moving towards electronics that aren't just smaller and faster, but fundamentally different, flexible, stable, potentially printable, integrated into the world in new ways.
So the final thought for you listening, as we see these ultra-stable, ultra-thin circuits becoming reality, powered by materials like WSE2, what completely new kinds of devices, maybe things we haven't even conceived of yet, could you imagine being built with them?